Hello and welcome to A Slice of Physics. I'm going to be talking about rectangle diagrams and how they relate to the hill analogy for electric fields. So first of all, let's talk about hills. So let's say that you have a ball and it rolls down a hill, and you know that there's some force pushing it down the hill. Well, you know that gravity is equal to the mass of the ball times g. That's the force pulling it down. But there's also a normal force that's perpendicular to the hill, normal force, and when you combine the two of them, it pulls the ball down the hill. So this force, this combined force, is F net. And the question is, what is F net? You can figure this out. The easiest way to do it is to see that the gravity force has a component that is along the hill, and it also has a component that is perpendicular to the hill. And this component in the direction of the hill is F gravity sine theta, if this is theta, and the component perpendicular to the hill is F gravity cosine theta. So this is the only part of the gravity that pulls the object down the hill, is force of gravity times sine theta, or mg sine theta. Another interesting fact that I won't prove is that sine theta is about equal to the slope of the hill. And that is true as long as the hill is not too steeply sloped. But most hills that you would walk up and down are not too steeply sloped, or that a ball would roll down. So what we have then is that the net force on the ball is about equal to mg times the slope of the hill. So just as a reminder, the slope of the hill is found by taking the rise over the run. So if this amount is delta h and this amount is delta x, then the slope is delta h over delta x. That's the slope. And so what we're left with is that F net is about equal to mg delta h over delta x, mg times the slope. And for a very steep hill, that will be delta h over delta x will be bigger, and for a shallow hill it will be smaller. Okay. And one more thing, and you know that for a steep hill, the ball is probably pulled down by a stronger force, so it makes sense for F net to become smaller when the hill is less steeply sloped. So what is the relationship between F net and the slope? Well, one way of writing it is that F net, when I divide F net by mg, I get the slope, which is delta h over delta x. Another way of saying that is when I multiply the slope by mg, I get F net. And another fact is that when I multiply the slope by delta x, what do I get? Well, the slope is delta h over delta x. So when I multiply that by delta x, I get delta h, the change in height, as something rolls down the hill. Now I'm going to take these two operations, the division by mg and the multiplication by delta x, and I'll put them over here. So I'm going to multiply F net by delta x. So when I multiply a force by the displacement, that gives me the work. So the work done is put into The work done by the force comes from, has to do with the change in potential energy, right? So as the force of gravity does work by pulling this thing down the hill, it does so by turning potential energy into kinetic energy. So the change in potential energy is the work, and that is equal to, we also know that that is equal to mg delta H, because mgh is the potential energy. So finally, if I were to divide the potential energy by mg, I would get delta H. So now we get this rectangular diagram with four quantities: F net, slope, delta H, and delta U. And these four quantities are related to each other by these arrows that tell you how you can get one from the other by multiplying something, by multiplying or dividing by something. Okay, so you might want to write down this diagram. You might want to pause this video and write down these four things, because they're going to come up in the next part, where I'm going to draw a similar diagram that's going to be about electric fields. But first of all, let me talk about the contour diagrams. So we have F net, slope, delta U, delta H, and F net, slope, delta U, and delta H. So if I were to draw a contour plot, let's say there was a hill that looked like this, then I would say that the delta H is the difference across, the difference in height across these two contour lines. So if I pick 2 points, then this delta H would be a certain thing, or I could find the delta H between these 2 points, right? Between any 2 points I can find the delta H. And I can also draw the slope arrows, which are longer where it's steeply sloped and shorter where it's shallowly sloped, right? So delta H is has to do with the contour lines, and the slope has to do with the arrows, which I call the gradient arrows. Okay. So let's do electric fields next. So to do electric fields, I'm just going to do the same thing. So there's going to be a particle, let's say a charged particle, and it's in some electric fields. So there's some electric field, and the particle experiences a force. So in this case, a positive charge put in an electric field will try to follow the field lines. It will experience a force in the direction of the field lines. So so the electric force is F, and if I divide by the charge Q, I get the electric field. So remember, the electric field is just the force that would exist on a test charge, but we divide out the charge of the test charge to get the electric field. Because for the electric field, we say that we don't know what charge is being affected by it. We divide out the charge. Then we know that the electric field, when we multiply it by delta X, we get the electric potential. So if these are two contours, then the distance between them is delta X, and there's some delta V, so it's actually delta V, some change in potential between these two contours, and the electric field times delta X will equal the change in potential across these contours. And of course there's contours everywhere, right, that are perpendicular to the electric field, just like the hill contours are perpendicular to the slope arrows. Okay? So then the force is multiplied by delta x, and when we do that, we get the change in electric potential energy. And when we divide the electric potential energy by Q, we get the electric potential. So once again, we have this rectangular diagram, and it looks very similar. It's just that instead of mg, we put q, and we have delta x there, and delta u is the same, and there's an f. So a lot of these components of this diagram are the same between the hill example and the electric field example. So let's do the diagram, a small version of the diagram again. So electric force, electric field, electric potential energy, and electric potential. And if I have, now these are potential contours, so maybe this is a 10-volt contour, and this is a 8-volt contour, and this is a 6-volt contour. Then these are the electric field arrows, and they're longer where the lines are closer together, and they're shorter where the lines are farther apart. So just as the slope arrows were the gradient arrows for the hill, the electric field arrows are the gradient arrows for the electric potential. And the electric potential plays the role of the height of the hill. And once again, we also have the force and the electric potential energy, whereas before it was the gravitational potential energy. So in summary, we've talked about the rectangle diagram for electric fields and hills. So for the hill, we had this formula that the net force was approximately equal to mg delta h over delta x, and that gave us a diagram that had net force, slope, change in height, and change in gravitational potential energy. And the electric field gave us a diagram that had electric force, electric field, the change in electric potential energy, and the change in the change in electric potential and the change in electric potential energy.